today's speaker is me, Singleton, so you probably know me. So I did my undergrad at MIT and I did my PhD at University of Virginia. I've been here since 1998. I've loved almost every minute. The only times I did like were when I had to do assessment reports. Other than that, everything's been gravy. Anyway, so today I'm going to tell you about a new look at Dirac's model of magnetic charge. And it's going to be kind of at a lower level, and so feel free to ask questions, okay? And so hopefully you'll learn something from this. So this is based on work with a former grad student, Michael Dunya, my former PhD advisor. It's posted on the archive. Let me say some bad stuff about the archive. So the archive, do you guys know what the archive is?
Yeah.
So recently they've become very draconian about who they let post and stuff. And so they basically, sometimes they'll not let you post at all, which is against the idea of a preprint. The preprint is you get your stuff out there and let people have a look. But apparently the people that run it are I don't know, they're bad. They're bad. They're bad. Anyway, so this is actually on the archive, but so a little bit of behind the scenes stuff. There's something called PhysGen archive, right? General physics. This is not general physics. This is particle physics, right? It's field theory, and so the PhysGen archive is the crackpot archive. So you guys know the term crackpot?
Yes.
Yes. It's not. If someone says, "Hey, you're a crackpot," it's not a good thing. But anyway. So, and actually my advisor, so I thought, well, it's just because I'm not at an R1. That's why it's happening to me. But my advisor is at an R1, and he was mad. He's like, what are you doing? This has never happened before. And I'm like, well, welcome to the world of not R1, all right? And also, let me give a shout out to Siva Mighty Lee. So she and I, my advisor, this is work in progress. So Siva, hopefully, in sometime this semester, we'll have something to submit to the archive, and hopefully they'll accept it to the regular archive. All right. So the talk outline is this. I'm going to tell you a little bit about magnetic charge and Maxwell's equations. I'm going to tell you about the quantum theory of magnetic charge. So the Dirac string potential. So how many of you have heard of Dirac string potential? Oh, great! You're gonna learn something new. All right. The Dirac quantization condition, this is why people get excited about magnetic charge. So they certainly don't get excited because we've seen it, because we haven't, right? But if magnetic charge exists, it gives an explanation for why charge is quantized, which we actually have no explanation for. Then I'm going to talk about field angular momentum and field momentum. So these systems contain field angular momentum and field momentum, which is really weird. And then I'm going to do summaries and conclusions. Okay. It kind of gives it away. Anyone know who this is? It says right there. Yeah. James Clerk Maxwell. Giant physics, basically the guy who formulated electricity and magnetism as a unified theory. E&M is the first unified theory. And basically after Maxwell, people are like, oh, I want to be like Maxwell. Let's keep on this path. Anyway, even Maxwell, very shortly after he put together his Maxwell's equations, he basically said, hey, it looks like there's room in these equations for a magnetic charge, okay? And so it's not a stretch at all. Well, Maxwell's a genius, but as soon as he formulated his equations, he was like, oh, look, here's the space for magnetic charge. So basically, if you add magnetic charges and sources to Maxwell's equations, they become dually symmetric, and this graphic explains that, and I'll explain it in a little bit. But basically, if you're a theorist, what dual symmetry means is you take every electric quantity and you change it for a magnetic quantity, and then you take every magnetic quantity and you change it for minus an electric quantity. That's the dual symmetry, and basically the general theme of 20th century physics is more symmetry is better. And so basically by having magnetic charge, you basically have introduced a dual symmetry, and that's, in theorist parlance, better, okay?
Now, is that negative sign make it symmetric? I mean...
Yeah, so you'd think it'd be just a one-to-one change,
Right.
but that's what this graphic is for, right?
Okay.
So I'm going to explain why you would need the minus sign, okay? So, also warning, this graphic below contains gross engineering units. All right. So basically what the dual symmetry is, you take all the electric quantities. Electric field goes to magnetic field, and actually it goes to C times magnetic field, which again, if I weren't using gross magnetic unit, or gross engineering units, that wouldn't be there, okay? And then you take the electric charge and you change it for magnetic charge, you take electric current, you make a magnetic current density out of it. And in reverse, you basically take magnetic field and change it to minus electric field. You change magnetic charge to minus electric charge density, and you take magnetic current density and you change it to minus electric current density. If you do this, right, basically under this thing, these equations become those equations, and these equations become those equations. So try it out. It's true. Okay, it's fairly straightforward.
So that's the beautiful symmetry.
That's the beautiful symmetry, right?
Exactly.
That basically the electric and magnetic fields then are basically two sides of the same coin. They're unified, right? And so again, more symmetry is better. And so this is the dual symmetry, and this is basically Maxwell's motivation for wanting to do this. Okay, so this is one of the most interesting characters in 20th century physics. So again, I kind of gave it away. This is Paul Dirac, right? He was, there's a book about him called The Strangest Man Who Ever Was, or something like that. And there are like quotes about him. Like there's a quote by Pauly that says, God, no, wait, hold on. Dirac has a religion, and his first postulate is that God does not exist, and that Dirac is his #1 apostle. So, so a very strange quote. And he's a strange guy. So there's a picture of him and Feynman at some conference in the late 40s, and Feynman spent like an hour haranguing Dirac, because Dirac was a god for him, right? He was like, and so he spent an hour expounding on path integral stuff, which is what Feynman's known for. And then at the end of the whole thing, so Feynman's like, hey, what do you think, Dirac? And he's like, Dirac says, oh, do you have an equation named after you? That's all he said. The end of the story. Anyway, so Dirac was the one who sort of looked at how quantum mechanics and magnetic charge fit together. So basically, he combined quantum theory and magnetic charge, and the PAM is Paul Adrien Maurice Dirac. So, and again, so the combination of combining magnetic charge and quantum mechanics led to his famous Dirac quantization condition. Okay, so let me tell you something that you hopefully know. So again, Feynman quote is, never underestimate the pleasure of telling people something that they already know. So hopefully you guys already know this. So anyway, what's an electric charge, or an electric monopole? It's something that has an electric field like this. So Q is the charge, it has the inverse squared radial electric field. That's what we mean. So furthermore, the electric charge is related to the Coulomb potential, and here's the Coulomb potential. It's Q times 1/r, and then if you take the gradient of that and put a minus sign in front of it, you get the electric field right here. Okay, great. Notice there's a point singularity here, so that's kind of a bad place in the theory. When R goes to 0, things go bad, but okay. So just notice that. Now the thing is, associated with this, there's this Maxwell equation. This is one of the Maxwell equations. This is in beautiful theorist units. So it's divergence of E equals 4 pi times the charge density. If you take this electric field, you take the divergence of it, then you actually will find out the rho you get here is basically Q, the charge, times the Dirac delta function. Now, how many of you guys have seen the Dirac delta function? Oh, great. So it's basically a function that's 0 everywhere, but it is infinite at a single point. So it basically represents a point charge. And so here's the cartoon graphic that I have. So basically you have a negative electric charge, has stuff, electric field lines going into it, positive has electric field lines going out of it. So with that introduction, you can probably guess what our idea of a magnetic monopole is. So a magnetic charge or magnetic monopole has magnetic field that goes like this. This is a typo, this should be G instead of Q, but I was doing a lot of cut and paste, so, okay. G is supposed to be magnetic charge, Q is electric charge.
Okay.
So the idea though is, it's exactly like the electric charge, but again, taking into account this dual symmetry, we just change electric to magnetic, and it should be a Coulomb field like this. Okay. Now, associated with this, if you take the divergence of this, that would tell you that basically the thing over here is not zero, that it's basically G times the Dirac delta function. So you have a single magnetic charge sitting there. And again, this is the dual case. So the dual case of my picture before is basically, so you have a north pole with magnetic field lines running away from it, right? That's the sort of magnetic equivalent of positive charge. And then basically you have a south pole, which has magnetic field lines running into it. And again, it has the same structure. It's radial, it's inverse squared, and that's it. Okay, I got these from different websites, so unfortunately these aren't colored as nice as the other ones. So, alrighty. Okay, what's the problem with that? The big problem is that basically at the level of the potentials, remember we talked about the scalar potential that gave us the electric field. Well, there's no scalar potential, Nathan. I'll answer those questions later. But conventionally, the magnetic field is just given by the curl of the vector potential. Okay, great. So, but it's a well-known mathematical fact that if you take the divergence of any curl, right, it's zero, unless the thing has some pathology, which we'll talk about. But anyway, if this is well behaved, then basically you take the divergence of this, and you will get zero. But that's at odds with what I had on the previous slide that said if I want a Coulomb magnetic field and I take the divergence, I should get almost zero, except I should get this Dirac delta function. So all these things are inconsistent with one another. So that's a theoretical inconsistency. Okay. Now also, at the end of the day, physics is an experimental science. So it doesn't matter how clever you are, how beautiful your theory is. If it's discrete in nature, it's garbage, right? So also, one of the more firm reasons for maybe not believing in magnetic monopoles is experimentally we only see these guys. We see a north and a south pole, we see dipoles, right? And we have like a dipole field. We've never seen anything like this, okay? So, all right, so again, it doesn't matter how beautiful your theory is, if it doesn't appear in nature, it's junk, okay? So, but Dirac was like, but it's so beautiful. Oh, and there's another quote by Dirac where he something about like God. So even though he was an atheist, he talked about God an awful lot, right? So he was like, God wrote the universe in the most beautiful equations he could find, and that was actually something that he internalized. He really felt that beautiful mathematics meant truth, and a lot of times it's been true. But sometimes you have to dig a little bit deeper than the surface beauty, right? So anyway, so Dirac proposed what are now called the famous Dirac string potentials. So basically, if you take this vector potential right here, and you take these two terms right here, so basically this right here, if you naively take the curl of this, you'll actually get a Coulomb field, okay? And basically, this is in spherical polar coordinates, and this is actually in cylindrical coordinates. I'm going to use cylindrical coordinates more later, but basically these are the same. If you do a transformation from spherical polar to cylindrical, you'll get this. This is a regularization term, and I'll explain what I mean by that in a moment. So let's take a look at this. Okay, well it has a 1 over r singularity, so it goes bad at r is equal to 0, just like the Coulomb field. Okay, so we're used to that. But now take a look at this. When theta is equal to 0, this, for the plus solution, and actually notice there are two solutions. It doesn't matter if you take plus or minus, they both give, when you take the curl, they both give a Coulomb field. But let's take the plus solution for the time being, and when you set the angle equal to 0, when we're along the positive z-axis, nothing goes bad. It's fine, right? Because you have 1 minus 1 over 0, but basically if you do a Taylor expansion of the cosine, the rate at which the top goes to 0 is faster than at the bottom, and so it basically has a good limit. However, if you choose the negative, well, let's do this. Let's take the negative z-axis, right? So theta is pi over 2. By pi over 2 I mean pi. So, so negative z-axis, so theta is equal to pi. So basically now you have 1 minus a minus 1, so you have 2. but the bottom is 0. So you have 2 divided by 0, and one thing we know for sure is that's going to blow up. So basically this gives you what's called a string singularity. So everywhere, for the plus solution, everywhere along the negative z-axis, the thing blows up. There's a string singularity. Similarly, for the minus solution, you can go through and you can show that basically everywhere along theta is equal to 0, or along the plus z-axis, it blows up. So you have this string singularity, right? You have this, it's not only a point singularity, everywhere along either the plus or minus z-axis, depending which solution you take, you're going to have a pathology, okay? Now, the thing is, Dirac regularized this by basically putting this term on here. So these are theta functions, basically theta functions or step functions. They're 1 when the argument is positive, and they're 0 when the argument goes negative. So basically here, notice this is 0, this is positive until you get like within an epsilon of the z-axis, or the rho. When rho goes to 0, you're close to the z-axis. So basically this is 1 until you get close, very close to the plus or minus z-axis. This basically tells you whether your singularity is along the plus or minus z-axis. And notice this is a rotating potential, right? It's a potential that goes around like so. Okay, physically what does this mean? Well, okay, I'm a theorist, so I like to show you equations. They're beautiful, right? So, but physically, if you look at what this means, it's as if you take a really tight solenoid, you wind it up, you send a flux through it, and you take one end of the solenoid and you send it to infinity, and the other solenoid then has a Coulomb magnetic field. I mean, imagine this is your solenoid, right? You have a north and a south pole here, right? And you'll have a dipole field. Now start stretching that end and make it go to infinity, and then the magnetic field that comes from here actually is a Coulomb field, okay? So that was Dirac's model, right? So you have this Coulomb field, and then you have this infinitesimally thin, but infinitely long magnetic solenoid that runs off.
That's what, go back that picture. That's what you're showing in that picture, at the end of that curled out solenoid right there.
Right, so this goes to infinity.
Right, and right there you're showing that point.
Right, and this is the mouth of the solenoid, and so basically, essentially a Coulomb field comes from there.
Right there, that's where I showed it.
Yeah.
So those field lines never connect back because they can never reach infinity?
Exactly,
Okay.
yeah. So basically, like in the limit, like if you had a north and south pole and you start stretching it, if you're really close, then it looks Coulomb, but then if you get further and further away, oh, you're like, oh, okay, actually it's coming, the return field is coming like this.
So it's not really spherically symmetrical at that location.
Right, right. So actually this does spoil the spherical symmetry if you could see this, okay? Now, but what Dirac says is like, okay, let me hide it. Let me hide it. And so, let me just say, okay, if you take the curl of those A's that I have then this is what you get. So basically, you get a Coulomb field, that's what we want, and then basically you get this solenoidal field. Notice it's in the z direction, so you have this magnetic flux, a magnetic flux of 4 pi g, and it's basically at x equals 0, y equals 0, so it's right on the z-axis, right? And then it's either along the negative z-axis or it's along the positive z-axis, right? So that's where the solenoid is, right? And so the first term is Coulomb, that's what we want. The second term is a solenoidal term, we don't want. We don't want to be able to sense this term, okay? And okay, so this basically just says this again. And this is where the Dirac quantization condition is going to come from. So now we only want this first term. That's the monopole term. So we want to make the string invisible, right? We're going to hide it. So one way to do this is basically, this implies that the Harnaff-Bohm phase is not detectable. Okay, so this would be a whole nother lecture. There's this effect called Harnaff-Bohm effect, where if you have a electric charge moving in a magnetic field, right, it will actually pick up a quantum phase, right? So, okay, so you're like, okay, sure. Like, he got a PhD degree, so you're like, for sure he's not gonna lie to me. But anyway, so the thing is, basically, this is a very famous paper, and it's a very, very cool effect because it showed that to some extent the potentials had more of a reality than you would give them credit for. Like, the classical view was, well, potentials are mathematical conveniences. They make things really nice for us to calculate with. But really, you don't you can get away, you can throw them away, right? You could do everything with the electric field, right? And actually what we measure are effects of electric and magnetic fields, not the potentials. The potentials have this sort of gauge freedom, okay? And so they're viewed as being not quite so real. But Arnoff and Bohm said, hey, wait a minute. Let's say you have an infinite solenoid. You have a magnetic flux. Now, for an infinite solenoid, you may know that the magnetic field is non-zero inside, but zero outside, right? So infinite solenoid, magnetic field constant, and non-zero inside the solenoid, but non-zero outside. So classically, if you send a charged particle in the vicinity of that solenoid, nothing should happen because there's no force for it to feel. That's it. However, the thing is, even though the magnetic field is zero out here for this situation that I've drawn here, the vector potential is not zero, okay? That's a little bit tricky. So basically, and in quantum mechanics, the charges don't couple directly to the magnetic field. What they do is they couple via minimal coupling to the vector potential. And so when the vector potential is non-zero, there exists this potential to pick up these Arnoff-Bohm phases, okay? And this is a very common and well-tested thing. So
that's a quantum effect then, right? Is that what you tell us?
Yeah,
Okay.
it's a quantum effect.
Quantum effect.
And it was first proposed, well, actually, so there's another, Side, like, actually almost 10 years, 20 years before Arnoff and Bohm had done this, but he didn't write it as beautifully. It was in a journal that people didn't read as much. But he had the basic idea, and then people didn't pay attention. But Arnoff and Bohm basically, independently, came up with this idea, wrote it up. They wrote much nicer, and they actually did point out, hey, you can test for this. This is something you can test for, and I think that's what Side, he didn't pick up on that. He was like, well, look, according to quantum mechanics, this and this and this, but he didn't propose a specific way to test for it. That's my understanding. And so Arnoff and Bohm get credit for it, although in their second article, that was a follow-on to this, they did cite Side, because Side said, hey guys, I thought about this before you. But, the world's unfair. Right? They were better writers, they published in a better journal, so everyone calls it the Arnoff-Bohm effect, right? So, anyway, in some sense it doesn't matter who discovers it. I guess if you're Sade and like you feel you got gypped out of a Nobel Prize, then you'd be like, well, hey, it matters quite a bit. But, okay. Actually, Arnoff and Bohm never won the Nobel Prize for this, although somebody should have won the Nobel Prize for this, right, Nathan? I mean, this is a huge effect, and it's very, very fundamental. Anyway.
So they have a closed loop integral? Because that's what's really novel, I think, in the AB effect, right? Do you know if Sade had a closed loop integral so that there is a magnetic flux?
That's I have to go back and look at the literature, but that was my understanding, is that except for specifically pointing to an experiment, right?
That's what I'm wondering. You said test. I mean, you make it an infinite solenoid, of course not. But are they trying to test this?
Okay. Well, how much time do I get?
Yeah, all right.
No. So the thing
I agree,
is,
that's for another time.
another reason this got picked up, Bohm and Arnoff, I think was his postdoc, they were at Princeton, they were at some fancy place. And they could just walk down the hall, and there's this guy Chambers who was working on electron interferometry. And he's like, hey, I have these like little fibers, these iron like hairs that basically I can put magnetic flux through, and we can stick that in the interference thing, so you would have a source of electrons. You would stick this like it's called an iron whisker. You stick it there, and then basically let's see what something happens. And that was in 1960. So in 1960, already boom, like there was evidence right there. You could clearly see the shit. However, people always have to hate, so they go. So they're like, well, it's not an infinite solenoid. You have an iron whisker, which has a very strong magnetic field inside the iron whisker and a very weak one outside, but the electron is not moving in a completely magnetic field-free region, so maybe it could be that magnetic field. And they're like, come on, it's so weak, blah, blah, blah. And they're like, well, no, but it could be, right? And so they didn't have a good answer. So now fast forward to 1984, there was a Japanese group, Tanamura, and basically they were really good at fabricating micro-nano rings. So they fabricated these tiny, first of all, they took the solenoid, infinite solenoid, which you can't have,
right,
and they bent it into a torus, right? So basically, and then they coated it with superconducting material, gold, like a bunch of stuff to make sure that no magnetic
Not in
flux
there,
could
right.
leak out.
Right.
And then they basically sent an electron beam through that like tiny micro ring. And basically there's this beautiful picture that clearly shows the shift in the interference pattern of the electrons that went through the center of the ring versus those that went outside. It's like, and then everyone's like, okay, that's it, done. Right?
So what you're getting at, this could affect a lot of things.
Oh yeah.
That's a quantum effect that does it, yeah.
It does. So it's a quantum effect, and yeah, it's very cool. So, and if you guys like this lecture, I can give a lecture on that. But actually, Nathan and I, that's the latest thing that we're working on. All right. So now, anyway, so I'm not going to explain where this comes from, but there's this well-established what's called an RF-Bohm phase, which is basically equal to this. So the wave function electron will be modified by this. Right? It'll have that on it. And this is basically the surface area interval of the string, right? So it measures the flux. This is the flux. And then I times the electric charge over h bar. And if you do this, again, this is just the flux, so you get a 4 pi g. What you do is you say, well, I don't want to see that. I don't want to see the effect of that. So basically what that means is I want the AB phase to be equal to 1. Okay, that's the idea. If the AB phase is 1, there's no effect. There's no phase shift, right? Now, what does that mean? So okay, so
I'm sorry, Doug, is that the same as saying it's 2 pi, so it just adds an additional?
Yeah. So actually, what it does is well here, all of this stuff up here minus the I bit, you want to be some integer multiple of 2 pi.
Okay.
Because E times 2 pi, any integer times I is always going to be 1, right? So that's the condition. So as you say, I don't want to be able to see the string. That means I don't want to see it on a bone phase.
It's like on a circle, you can't tell you went through an additional revolution.
Yeah.
If you land at the same spot again.
Exactly.
Right?
Exactly. So anyway, so you set all this except for the I. You set that equal to 2 pi times some integer, and then if you do some simple calculations, you find that what this requires is that the electric charge times the magnetic charge is some integer multiple of h bar over 2. Okay, beautiful. All right, so this is the famous Dirac quantization condition. So look upon it and admire, okay? And also the most serious thing is though, it gives a motivation for charge quantization. So what's the charge of the electron? P.
In gross engineering units.
In cool.
1.6
times 10 to the negative 19.
Yeah, there you go.
Last Harrison.
Well, no, one is
Don't ask a fellow theorist that question. Yes, you're going to get one for everything.
It's H bar 1. Okay. Anyway, so yeah, why? Why is it that? Like, and all charges seem to come in like those multiples. We have no explanation for why that is. This would actually be something in the direction of that, because this is it's a quantization of the product of electric and magnetic charge. That's fantastic. It would give us an explanation for why is that, right? And these are the papers that Dirac wrote. So he had some initial idea, and then he thought about it, and then he wrote another paper on the same thing. Okay. So, and again, the idea is you have electric charge, you have a monopole, you have this string, and basically, by requiring that the string is invisible, you get this condition. Fantastic. Okay? So, wait. All right. All right. So now I'm going to tell you something else. So there's another way to arrive at the Dirac quantization condition. So surprisingly, right, I love this idea. And like when I first encountered it as a grad student, I was like, well, that's weird. Right? Surprisingly, the system of a monopole and a charge has a non-zero field angular momentum even if nothing is moving. They sit there, and there's some angular momentum in the electromagnetic fields. Wow. Right? So Paul's scrunching his face up, and yeah, it's like, so what's the calculation? So you take the Poynting flux, which is basically the momentum density. You take the momentum density, you cross it into R. Now you have the angular momentum density. Now you integrate that thing. Now here in this picture, what I've done is I've taken the monopole at the origin. The electric charge is at some arbitrary vector, which I'm going to call R vector naught. That's where the electric charge is located. Now, if you do this calculation, and it's not trivial, right, Mighty Lee? We're working through it. You actually get a very simple answer. You get minus QG times the unit vector that points from the electric charge to the monopole, right? So, and notice this immediately gives you another avenue for getting the Dirac quantization condition, because what do we know from quantum mechanics? All angular momenta are quantized in integer multiples of h bar over 2. So basically, by setting the magnitude of this to integer multiple of h bar over 2, you get immediately the Dirac quantization condition that I had on the previous slide, right? Beautiful, right? So whenever you come to the same result via different methods, it gives you, it's like, oh, cool.
The symmetry of the universe, is what it is.
Yeah. So I mean, and Dirac was really drawn to this, and you can see why, right? Anyway, here's another sort of interesting fun fact. That's not really, I'm not going to really use in my lecture, but if you have a gravitational Coulomb field, right, sun and a single planet, so in inverse square force law, what kind of orbits do you have if the orbits are closed? Elliptical or circular, right? And then if they're open orbits, it's parabola or hyperbola. So those are it. But for closed orbits, it's basically circle or ellipse. Now, the thing is, then you can ask the same question. Well, if you have an electron or an electric charge orbiting a monopole, what are those orbits? It turns out there are no closed orbits for that system. But it does a really interesting thing. Basically, the charge will move on the surface of a cone, and the cone depends on the initial velocity of the electron, and it doesn't depend on the, well, it does depend on the charges, but the charges are already fixed by the Dirac quantization condition. So this is a really weird thing. So these are the orbits, right? If you send an electron in, depending on its initial velocity, it'll form some kind of conic orbits. Not closed, right? It'll come in, spiral around, and then spiral out, but it stays on the surface of a cone. Okay? All right. So now here's the sad thing. So, and this is the thing that's overlooked, and this is the thing that we claim is new to our thing. If you take the magnetic field of the string, so you take and you do, cross that with the electric field. So here's the Coulomb electric field. Here's the string magnetic field, and here we're going to cross it with R to get an angular momentum density. If you integrate this is a dead simple integration. And so I had to do this a couple times because like for sure it's going to be 0. I originally thought it was going to be 0 just because the string is infinitesimally thin, so it has like 0 support, but it's also infinitely long. And so those two things sort of counterbalance each other. And I did this calculation a lot of times because like it's got to be wrong, but it's not. So there's a contribution here. So actually, the total angular momentum of the system is not just between the Coulomb electric charge and Coulomb magnetic charge, but there's also a contribution that comes from the string. Okay? So really, the total angular momentum, you should take this piece, you should add it to the point piece, and now the total angular momentum becomes either this expression or this expression, right? And so, well, first of all, like let's say you can actually have the total angular momentum completely vanish, and that actually might be good, right? Because then somehow the angular momentum of the string and the angular momentum of the point part go away, which is actually kind of what you expect for like naively, right? But also if you take this close to like say 0, or wait, where's secant is 1 over cosine. So if you take this close to pi, right, this is going to blow up. And so basically, as you take the angle around, as you take the charge around, the magnitude of the total angular momentum can go all the way from 0 to almost infinity, or actually approaching infinity. So
that'll sound good.
It does. It's not good at all. So the thing is, so this is not good for the Dirac quantization condition, because basically, at least in this way, you lose one of the paths to achieve the Dirac quantization condition. So that's bad. And we've looked a little bit more into this, into the paper with Michael Dunya and my advisor PQ. We actually show that if you take the string piece, the point piece, and the mechanical piece, and you put them all together and you see if they satisfy the standard commutation relationships, they actually do satisfy those. So in some sense you might say, well, this sort of, taking the total angular momentum, taking the magnitude and setting it to n h bar over 2, that's kind of naive, right? That's what you say whenever anything doesn't work out. If it doesn't work out, you're like, oh, that's too naive, right? And so if it does work out, you're like, oh, good job, right? But anyway, it is true. This is more, just doing this is sort of naive. and we were able to show that if you take the commutation relationship, it does satisfy even when you add the string piece in. However, right, this is what we think is the death knell for so what I want to say is Dirac monopoles are probably out, right? So which is a big statement, but
right, I was going to say, yeah.
So anyway, so now on to the field momentum. Okay, so these systems have field angular momentum. Well, what about field momentum, right? So actually, those are that's even easier to calculate. Instead of basically doing the integral of r cross e cross b, you just e cross b. That's the momentum density, and you integrate that. Good thing for the point part. So if you take the Coulomb part from the electric field, you take the Coulomb part from the magnetic field. And again, here I've taken the magnetic charge and I put it at the origin. I've taken the electric charge and put it at some not origin place called R naught. You run through this, you do the calculation, you get 0. That's good, right? But you do the same thing for the string part and you get not 0, right? You can get 0, for example, if you look at a special location, like you put x and y at the origin, you can make it, but in general it's not 0. So this is bad because basically, like, and why is it bad? Well, basically having a non-zero field momentum violates the center of energy theorem, right? And so basically, what is the center of energy theorem? It says basically the center of energy of any closed system is at rest, then its total momentum is 0. So the system is definitely at rest. The total momentum should be 0. All the mechanical pieces are at rest, right? So, but this is bad. So we apparently violate the center of energy of a closed system. And actually, this goes back to a paper by Coleman and Van Vleck on the origin of hidden momentum forces on magnets. And this paper was actually in response to a paper by Shockley. Oh God, I forget who. He had a co-author. But Shockley won a Nobel Prize, so I forgot who the co-author was. That's kind of crappy, but okay, it is what it is. So they wrote a PRL, and they basically looked at a magnet, and the magnet was losing its magnetization. So it was magnetized and then going to 0 in the presence of an electric field. And then basically, originally nothing was moving, and suddenly the system started moving, but without any back reaction. So it looked like momentum conservation was violated. So bad. So basically, that's the kind of thing that this implies, is that basically momentum conservation is at risk, and that's no good. So so what? Well, the thing is, now there is a potential for what's called hidden momentum. So again, the fact that the system has a field momentum, right, is not necessarily bad if you can find some compensating momentum to balance that so that the total momentum is 0 according to the center of energy theorem, which comes from special relativity. So that would be great. So actually, this is an example from Griffiths. So have any of you suffered through Griffiths with me? Okay. Okay. Oh, yeah, that's true. Okay, 20 years ago. All right. So, well, hopefully this doesn't give you guys flashbacks. Okay. All right. So basically, consider the figure below. So I'm going to explain where hidden momentum comes from. So I'm going to take a break from fantasy stuff. This is actually real stuff. Okay. You have a loop, right? You have charges moving around the loop. The loop has a length L with W. There's an electric field going up all this way on the board. So it's electric field this way. And these are charges, right? And now notice, because you have an electric field here, basically the charges are moving along here, but they get accelerated here, and then basically so they're moving faster. Now notice that the charges have to spread out here. The current has to be continuous throughout. If the current's not continuous throughout, then there's going to be buildup. There's going to be buildup somewhere. So basically, since these guys are moving faster here, because of the electric field, they have to spread out, right? So in other words, what you want is you want the current to be the same all the way around, right? Now, one of the things you can do is you can say, well, this current produces a magnetic field, and actually produces a magnetic moment. If you calculate the electromagnetic field momentum in this system, and it's not an easy calculation, but if you do, you find out that the field momentum in the electromagnetic fields, right, is equal to minus the magnetic moment of this system cross the electric field. So I mean, To get to this point, you have to do a bunch of integrations, but this is the final result. It's very beautiful. And you get this, right? You get minus the current times the length times the width times the strength of the electric field in the x direction, x hat direction. X hat direction is in, well, x is in this direction, so this field momentum is actually this way. It's that way. Okay. Now, classically, the total momentum of the particles, what are those, right? Well, classically, it's basically 0. Again, why? So here it's, the momentum is mass times velocity, and this is number of particles per unit length. This number of particles per unit length in the top times the velocity in the top minus number of particles in the bottom times the velocity in the bottom. Okay? And now the velocity in the bottom is less, but the number density is bigger. And here the number density is less, but the velocity is bigger. And if you convert number density and velocity into current, the length of this thing, and the charge right here, right? So that basically what I've done, or what Griffiths does, is he converts number density times velocity into current times length times charge. You find in order for the current, or for charge not to build up anywhere, this n sub t vt has to be the same as this, and so you get 0. Okay? That's classically what you expect, and great. But relativistically, that's not the case, right? Because relativistically, momentum is not just mv, but it's gamma mv. And so now the gammas are also different in the top and bottom because they're moving at different velocities. So basically, the relativistic momentum here is not 0, but it's actually this guy, right here. Okay? So remember that expression. And then, now if you look at this, basically this quantity right here, basically the gamma factor for the top times the rest mass energy of the particles minus the gamma factor at the bottom, that's the change in energy. And by the work energy theorem, that's just equal to force times the distance over which it's moved, right? So this is change in energy times basically force times distance. And then if you take this expression and you basically solve it for gamma t minus gamma b and stick that up into the previous expression, so let me do that again. So this is just work energy, and then I basically take that gamma t and stick it back here. And then if I calculate, then basically there's actually momentum. And this is momentum in the particles, because I'm messing with the particles now, right? Talking about the mass of the particles, the velocity of the particles, all that. Basically that ends up being plus the current times basically the length of the thing, the width of the loop, times this, times x hat, but in the plus direction, again, so here I have c not equal to 0, or not equal to 1, here I set it back equal to 1. So, but notice this is plus, now if you add these two together, you get 0, that's exactly what you would expect. So this is how a lot of these hidden momentum things work out. The field seems to have a momentum, that violates the center of energy theorem. But then if you dig deeply into the system, this is very subtle, you find out, oh, actually there's some relativistic effect that gives the momentum of the particles that balances that field momentum. Great. Okay? So, well, that's going to be the answer to the momentum in the magnetic case, the magnetic monopole case. So there's got to be some hidden field momentum. And sure enough, there is. Like if you take that B field, the Coulomb part plus the string part, you take the curl of it. Now, basically the Coulomb part, since it's radially symmetric, the curl of that's going to be 0. But basically the string part will give you something, and it'll give you this. So there is some current density. It's going to be embedded in an electric field. So there is actually some hidden momentum in this. So you're like, okay, well, that's it. There's got to be some hidden momentum in this that balances the field momentum. But if you go that route, then you've already lost, because that means the string is real, because there has to be some basic real current connected with it. So either you violate the center of energy theorem, which violates special relativity, which is kind of bad, or you go like, oh, no, I know how to fix this up. It's going to be hidden momentum, and the hidden momentum is going to reside in the string. But then you have to admit that the string is real. So, you know, so what's, Fred, you're gonna, in the Odyssey, they sail between two rocks, Scylla and Charybdis. Come on, come on, guys. Somebody has to know like classical Greek literature. Anyway, let's just go with that.
Italian names.
What now?
I know the Italian
Oh,
names.
Scylla and Charybdis, right? Oh, yeah, okay. So basically, you have a choice of like either one monster or the other monster. Okay, anyway, so that's the end of the talk. So basically, what did I do? I reviewed Dirac magnetic monopoles, okay? And so basically they're in textbooks. They're in Jackson, they're in Griffiths. So I mean, you'll encounter these. And again, you might say, well, we don't see these things. So why, for God's sake, why? And the thing is, again, textbooks are generally written by theorists, and theorists love beauty, and so extra symmetry means beauty. So, okay, and yeah, so extra dual symmetry plus and charge quantization. So that's actually something that we know is true. Dual symmetry is just a beauty thing, but we know charge is quantized, right? And so if we could get an explanation for it, that's worth something. Okay? So, but the point I wanted to make here is the contribution we're making is there's an overlooked string contribution to the field momentum and field angular momentum. You can kind of fix that up, but only by admitting that the string is real, and then you've already lost. Okay? So, anyway, the conclusion is the string is either real, and then you're already lost, or we're going to violate special relativity. Okay, so thanks a lot.
All right.
So questions?
Yes.
Oh,
Are you making a magnetic monopole right now?
Right now?
Yeah.
No.
Is there, I mean, when I say right now, I mean, is it possible to make it?
Okay, so there's actually a group called Model, which is at the Large Hadron Collider, and they're actually actively looking for monopoles, right? And now the thing is, there are other types of monopoles. There's these things called Tuff-Polyakov monopoles, which, okay, that's another lecture.
Right.
And but basically, in the Tuff-Polyakov monopoles, what they do is they have some of the flavor of the Dirac string monopole, but the string is actually smoothed away. They don't have the string, but they replace it by a scalar field. But the scalar field has to have this weird, what's called a hedgehog configuration. So the scalar field, scalar
It looks
field.
like it's got circular symmetry there.
Yeah, so it has this weird sort of what's called a hedgehog configuration. So this was from, these are called Tuff-Polyakov monopoles, and basically from far away, they look like a monopole, but when you get close to them, they actually have structure. So actually they're very nice. So the unfortunate thing is, if these guys exist, they're like 10 to the 12 GeV or 10 to the 15 GeV in mass. Okay,
Oh.
so our current accelerators go up to like, I think, 1,000 GeV, 10,000 GeV, 10 to the 6 GeV. So that's like many orders of magnitude above where we have reached to get. So basically, to create these kind of beasts, you would need accelerators that are just way beyond our capacity now, right? So, but for the Dirac monopole, there's no limit, right? So because it's, again, the theory is less sort of refined, less constrained. So these things, because you have to include the scalar field, you have to take that into account, and that basically puts this sort of mass constraint on these things. But anyway, people still look for monopoles, and as far as we know, something like a Dirac monopole, or like not a Dirac monopole, but a Tuff-Polyakov monopole should exist. They're just so heavy that you can't make them. There is something also in cosmology called the monopole problem, because you're like, okay, well, when was there a time when there wasn't enough energy to create such a thing? Well, in the early universe, there was a ton of energy, and so basically monopoles, these Tuff-Polyakov type monopoles, should have been created copiously, right? And they should actually still be around. And so basically what you do is you set up a superconducting loop, you wait for one of these things to go through. Basically there's a change in flux that basically turns on a current. Because it's a superconducting loop, the current doesn't go away, so you can go and come back and look and you go, oh, there's a quantized current that's now flowing in this, a monopole must have passed through. And so that's how people actually look for these things. And I think that's more or less how Model look. Like some more advanced version of that, but that's essentially how they look for these things. But, and again, if the Tuff-Polyakov monopoles were left over from early universe, then that's how you would look for them. I mean, to create them is beyond our capability right now. Now, there was a guy at Stanford, Blas Cabreras, who actually set up such an experiment, because it's not that hard to set up. You just take a superconducting loop, put like an ammeter on it, and then you should wait. Right? So it's one of
That's
those
the
like,
biggest thing,
yeah,
yeah.
you just wait. And actually, Valentine's Day, 1981 or 1982 or 83, early 80s, right? He went to lunch, came back, oh, there's a signal, right? And so then he was like, yay! And then, but you know what, in science, you need reproducibility. So like, oh yeah, well, so we should see another one of these signals. So they set the experiment up, ran it for 10 more years, 15 more years, they didn't see anything. So they're like, oh, that's so. And then people ask them like, hey, you know, actually, maybe the single loop was not a good idea. Maybe you should have a stack of these things, right? Because with a single loop, maybe someone bumps it, something happened, you know, a temperature fluctuation, who knows, right? But if you have a stack of these things and they all pick up the same, like, quantized current, okay, he's like, oh, yeah, I should have done that. But anyway, so that, and the thing is, there's now currently an explanation. So if you do calculations of early universal cosmology, basically two-poly monopoles should be around, like we should see them a lot, right? But we don't. So then people have an explanation for that too, which is called inflation, right?
Yeah.
So basically, at the early universe, there was this rapid expansion so that any of the monopoles that were created were diluted to the point where they're essentially undetectable at this point. And so then you're like, okay, all right, I see where this is going. Yeah.
So a lot of the mathematical complication I noticed came out of trying to have a vector potential that has a curl and can still give you a monopole. Is there a reason why Dirac didn't go the route of the scalar potential? I know you kind of referred to me at that point, because it seems like so much of the mathematical complication, like if you back up to one of the earlier slides where you first wrote down that vector potential and had all those terms that you were analyzing, you're saying this is what we have to have because we have to have basically a way of stretching the one end of the solenoid to infinity and the other is going to give us our monopole and so forth. Why didn't he just go with the magnetic scalar potential route?
I don't know. So that's a good question. So again, Dirac maybe it was for the reason that he only saw one massless photon. So what Nathan and I had a discussion beforehand. So there's another way to introduce magnetic charge, and it's like this. So you have an electric field, magnetic field. Now the standard thing is, and here, maybe I turn the lights on. Is that better?
Yes.
Okay, so then, okay, so you guys recognize this. This is basically, I have a vector potential. It's actually 4 vector potential, which is basically a scalar potential and a vector potential. And the electric and magnetic fields are basically these, like this, okay? And so, so here's this, and actually for this talk, I only used this because I wasn't thinking of dynamics at all, right? So I didn't have any time changing stuff. So I only had this and this, right? But what you could do, you could look at this and you could say, oh, well, another way to go is actually to introduce a second 4-vector potential, like this. And then classically what you do is you basically add just like this, and then like this. And the minus sign here versus here is connected with the duality, right? It's not like electric goes to magnetic, magnetic goes to electric. It's like electric goes to magnetic, magnetic goes to minus electric. So that's the reason for this. So this satisfies that dual symmetry, right? And so Nathan's question, and I think that this is still your question, is like, well, why didn't Dirac go
the
this
phi
way?
m right there would have solved it all, right? The phi m.
Yeah.
Yeah.
So this would
you wouldn't
really
have had to
solve
go to
the
that really complicated vector potential expression that led to the string and so
problem. Right. Because then what you could do is you could say to get a magnetic monopole, all you have to do is basically go G over R, just the same way you do for the electric thing.
Yeah.
However, if you take a look at this, when you go to quantum theory, this makes photons, right? When you quantize your theory, quantizing these become photons, right? And photons are massless, and you should be able to see, and we're able to see photons easily, right? That's how we're seeing everything right now. And so the thing is, if this is also a photon-like thing, then we have 2 massless photons, right? And the thing is, these have different CP properties. So you might say, well, maybe they're the same photon. They're not, because basically they have to have different CP, they have different behaviors under CP, under charge conjugation and parity, so they behave differently. Like this is a regular vector under parity, this is a pseudo vector, right? And what a regular vector does under parity is if you have a mirror and you have a regular vector, then the reflection of it basically comes back out, whereas a pseudo vector is the reflection actually points in the same direction, right? So, so they would be different, and they would both be massless, and so we don't see a CP odd massless second photon. So that's why we get rid of that, right? And then I was also telling Nick, actually, in grad school, I was looking at Dirac stuff. Actually, I was looking at Polyakov stuff, and then I went back to Dirac. And I said, yeah, why you can do this, right? And so why not? And then I was, well, because you'd have another massless photon. And then, but then, like in modern particle physics, we know the Higgs mechanism. The Higgs mechanism is a way of breaking symmetry, giving mass to gauge bosons, and then basically they become invisible until you reach the energy scale that's basically associated with that mass scale. And so what you do is you apply symmetry breaking, and then you make this thing massive, you make this photon, this magnetic photon, massive enough that you don't see it up to some energy scale. Right.
Well, question about that. If you were to just do a classical calculation, or like in our upper division E&M, where you just show that you get a wave for E and a wave for B, wouldn't you still get classical electromagnetic waves just the same out of that full set of equations you have on the board there? In other words, you don't have to bring quantum into the discussion. Wouldn't you still get electromagnetic waves that look just the same? Box E and box B is what I'm saying?
Yeah, yeah.
So
actually, at the classical level, that's true. Yeah, actually, I have to think about that because they're still the two potentials are still.
And it still goes at the speed of light too, right?
Yeah. So absent giving a massless thing, they would both move at the speed of light. You know, everything.
Maybe that deserves a separate, consideration.
But we know they have to be quantized. We know they have to be quantized. So basically, I mean, inevitably there would be, so, but yeah. So when I wrote this paper and I published it in HAP, like I got a lot of things like, oh, that's a dumb way to do stuff. I got emails, right? Like, everybody knows you have to do magnetic charge via the Dirac. I'm like, oh, okay. Because, but there are other people who worked on this. Actually, Abdullah Salam worked on it, and but yeah, it's actually Schwinger even worked on this. But it really never caught on for some reason. I don't know why. So I think this is more, this is better, right? But again, the thing is the masslessness, at least unless you do something like symmetry breaking, the masslessness of this magnetic photon is bad. It basically would invalidate this theory, right? But again, it's the same reason I was telling you when Yang from Yang-Mills, he formulated the Yang-Mills equations, which are sort of nonlinear versions of Maxwell's equations, and then he gives some lecture, and then Pauli stood up and goes like, oh, your theory is worthless, because basically if you're correct, there's going to be these massless gauge bosons all over the place. They're not there, so you can just stop talking. So Pauli he's a funny guy. He's like very smart at a very young age, but he had very strong opinions, and he was often right, but he was often like super wrong, right? And that was one of the cases where he was wrong, because he nor Yang knew about symmetry breaking, right? So, but anyway, yeah, you can go this route, but even today, the Dirac string potential is like the more common, more accepted route. So, and what we want to say is like, well, hey, maybe there's some issues with the Dirac approach. And again, there's a whole collaboration called Model that looks for monopoles and exotics at the LHC. They still haven't seen it, so I mean, maybe the reason why is because that they aren't there, and this is a theoretical reason why they don't exist.
Hey, real quick, I'm gonna do Doug's job, you guys. So if anybody wants to hang around and talk to it, I gotta run. I don't want to be rude about it anyway. I think we ought to thank you for that talk.
Yeah.
Exactly.
All right. So do you guys want? Okay. I'm game. Good, son.
Yeah, your charge times the magnetic charge, that NH divided by 2, is that N can be 0 or not?
Yeah, so if it's 0, then like I can stop talking.
Oh.
Yeah, so,
Oh, okay.
so yeah.
No, it's kind of that H divided by 2 remind me that Heisenberg uncertainty principle.
Yeah. I mean, like, but all spin is quantized in h bar over 2, right? I mean, the electron has magnitude spin, well, has spin h bar over 2. Photon has spin h bar. Graviton has spin 2 h bar, right?
No, but does there any kind of uncertainty principle need to satisfy here?
No.
Okay. Second question. So just say experimentally, I heard about in the black hole, there's a part you will stretch infinite, like a human going to there, you will stretch infinitely long in
Yeah.
that frame.
Yeah. So
Will you be able to produce in that monopole there?
Oh.
Yeah.
No. So. Yeah. Okay, so black holes basically give off radiation, Hawking radiation.
But that's outside. I'm talking about inside.
Okay, so yeah, so the thing is like, as you get closer and closer to the event horizon, basically you'll cook up particles, but the only ones that basically are able to radiate away as Hawking radiation are basically massless or effectively massless. So to see like any monopoles created by this, right, you'd have to go very close to the event horizon and then probably get sucked in. So yeah, if you go inside a black hole, maybe the gravitational fields there become strong enough that they can basically rip the vacuum apart and start popping out like, you know, monopole, anti-monopole pairs. But if it happens under the event horizon, then it doesn't matter, right? There could be angels dancing, there could be like anything happening under the event horizon and we don't know.
Because even the CERN can create a micro black hole or something.
Some theorists thought of that. Some theorists thought of that.
Huh?
It is, so yeah, so no, back in the late 90s, early 2000s, like Arkani Ahmed and other people had this modified way of modifying gravity that made gravity become much more strongly coupled at distances or at energy scales that we have access to. And you know, those theories could have been true, and if they were true, what would happen is you would actually be able to create black holes at like the LHC, right? Turns out they've looked and they've bumped the energy up, they haven't seen them. So what they've done is they put limits on those theories, right? Yeah, so it's not bad theory, right? You make a guess.
I don't know. I'm experimentalist, condensed matter. I completely have no idea. That's why I asked you.
Oh, actually, so I have something for you. So you may have read in Nature. This is actually 5, 6, 7 years ago that they actually did discover a monopole in spin ice systems. Have you ever heard of spin ices?
Spin liquid? No.
So there's some kind of like weird. There's some kind of weird like system. And they don't have like a really good structure, but they have these links like this, and then along each of the links there's like a magnetic dipole. They're a little bit different color. And along, so there's some kind of like asymmetric lattice, and then along each of these lattice links there's like a magnetic dipole. And you can have these chains that run like this. And then this end right here basically is an uncanceled north, right? And so basically this dipole here, the south, is canceled with this north and so forth. And so effectively it's like a condensed matter version of the Dirac string, right? And so basically the thing is, like these links are all atomic scale, right? And these can run for like several centimeters, these things. So basically, for something that's atomic scale size, if you run a centimeter away, that's effectively infinity, right? And so basically these spin ices, they made a big splash in Nature and Science and stuff like that. People wrote about them like, hey, like we discovered condensed matter monopoles. But again, they don't satisfy the Dirac quantization condition, so they're sort of effective monopoles, right? They're not fundamental, right?
So has anyone actually done any real work on like, let's assume these charges are really real, these magnetic charges are real. Let's look at, say, the Coulomb problem in quantum. Like, does anyone do something like that? Do you basically get the same results, or like weird stuff happen that you should be able to maybe see in reality?
What do you mean the Coulomb?
Like a hydrogenic atom or something. So you have like a positive magnetic charge, negative charge, kind of fix one. What happens there?
Oh, yeah. So there's a problem here. So actually, if you look at the Dirac quantization condition, right? You look at this. Okay. So you take a look at that, and let me see. You can actually ask, well, how strong is the magnetic interaction, right? And if you take a look at that, the magnetic charge basically is proportional to 1 over the electric charge, right? Then you can ask, well, how strong is this magnetic interaction? Well, if you have dimensions and stuff, you can't make heads or tails out of it. Like, I mean, is something strong or weak? What depends what units you use. But there is actually a dimensionless way to figure out how strong something is, and that's by the fine structure constant. And the fine structure constant, I'll put a sub E for electric, is basically the electric charge squared over h bar c. And actually, depending on the units, it could have a 4 pi or an epsilon naught, but gross, right? So this is about 1 over 137. So you guys have heard like that fine structure constant, right? So you can make a fine structure constant. So you can say, well, roughly how strong is the magnetic charge? So you can make a magnetic fine structure constant, and you can go g squared over h bar c. But because of this inverse relationship, instead of being 1 over 137, this is 137. So basically, it's the reason we're able to quantize electrodynamics is because basically when you calculate higher order diagrams, they're all done in expansions of this. So like the first order is order 1. The next is going to be this order. The next is that order squared. So all the terms get smaller and smaller. So basically the series, well actually there's an issue about convergence, but you can cut it off, right? You can cut the series off at some point and go like, okay, the higher terms aren't going to be an issue, so good. But here it's horrible, right? Every higher order term is like contributes more than the one before it. So you can't really do perturbation theory in that sense. So basically, this is if magnetic charges existed, they would be what's called a strongly coupled theory, and we don't know how to deal with those. So we know how to do perturbation theory. So basically, something that basically becomes weaker and weaker. So you take higher orders. This actually does the very opposite. Every order becomes harder and harder. And we actually have to face that problem for real with the strong interaction, so you can basically, what am I going to do? H. No, H is not good, because I'm using H bar. Let's say F, okay? Let's say the strong coupling is F, right? So you can just define the strong coupling constant as basically F squared over H bar C, and that's anywhere from like 1 to 10, right? So, and that's already bad enough. So basically people say, well, you can't do perturbation theory on the strong interaction at low energies. We have to figure out some non-perturbative things. And that's when the coupling, this alpha, is between 1 and 10. So this is like super strong. So it's not just strong, it's super strong. So anyway, but that's because of the quantization condition, right? And because this alpha sub E is perturbatively small, that means that alpha sub G, the similar thing for magnetic charge, is non-perturbatively large, and we really don't know how to calculate with that. So even doing something like, okay, calculate for me the equivalent of the hydrogen atom, but with magnetic charges. Yeah. Like, the thing is, what helps us with like calculating the hydrogen atom for like real electric charge and real proton is it's a weakly coupled theory, so basically you can ignore higher order terms. You can't do that with the magnetic case. So it's just horrible. If they existed. So that, then you might go like, well, God, thank God they don't exist, because then we don't have to deal with them, right?
I mean, I like the classical Maxwell equation result, because the difference between magnetic and electric field is just motion, no? I mean, you have a charge. So, I mean, magnetic monopole would actually complicate. I mean, it's symmetry just on the equation side of it. But if you see seek about, what's the difference between, it's just the motion of the on charge.
Well, nature seems to agree with you. So that at the end of the day, it's, yeah. But yeah, so,
Can I ask something that might be a little bizarre, but if you think about gravitational charge is essentially mass, you could say that, right? So mass is the coupling parameter for gravity, electric charge is the coupling parameter for the electric field, and this magnetic charge is the coupling parameter for the magnetic field, etc. So we know that a particle can contain both mass and electric charge, like an electron after all. So in a sense then it has both coupling parameters associated with it. Is there any reason why we couldn't have both the electric and magnetic coupling charge associated with a single particle? Or is that
so
forbidden?
those are called dyons after Freeman Dyson.
Oh, so this has been
Yeah, so
thought.
they
Thought of. Everything's been thought.
So, Mihai, back to your question. So monopoles are very good for at least one thing, allowing theorists to write papers. But yeah, no, but people, yeah, so there's all like variations of this where like Schwinger was the one who actually looked at, well, I guess Freeman Dyson was the first one, but then Schwinger really picked up on this and looked at, systems that had electric and magnetic charge, right? Or like single particle that had both electric and magnetic charge on it, right? And they're called dyons.
Are they actively trying to find them?
Well, they're like the Model collaboration. I mean, this is like $1 million plus like collaboration, and my advisor's part of it. And it's like I think it's not one of those big collaborations like Yongsheng is part of it. It's like 3,000 people, but it's like 50 people. But even that, like as a theorist, right? Like you're like a collaboration of 50 people. What the hell? That's big. That's big. Yeah. But for theorists, but like for experimental group, that's like not so big. But they're actually actively trying to look for these things. Yeah.
So you call it quantity of electric charge Coulomb. Is there a name for the quantity of magnetic charge? No one's come up with a name for something that doesn't exist.
Call it a Singleton, since it's a model.
Yeah, I mean, it would probably be like the Dirac or something like that.
Well, you could use the units of Planck's constant and the units of Coulomb and construct it, and so then it would just be giving it a new name if you wanted to, right? Because it's on the right, you got the units of Planck's constant on the right, and on the left side you've got the units of electric charge and magnetic charge, so.
Yeah, Planck's constant squared. Or square rooted, not squared.
But like in the covariant idea, shouldn't it happen that if a monopole is in motion, it should generate maybe an electric field?
Oh yeah. That's what the equations tell you, right? So like if
interesting.
So a moving magnetic charge would have sort of the circulating electric field. So I mean,
So if
again,
it passes by an electron, the electron will start radiating
Yeah.
like radial.
That's what that C vector will do for you.
Interesting.
so any other questions? For you?
Some connection to dark matter problems like, let's say, monopole, quasi-crystals, stars, as such paper in the literature or not?
So that's one of the things my advisor and I were actually looking at. So he's interested in dark matter, and so basically, well, another reason maybe monopoles don't occur is, well, they're strongly coupled. So like color charge from the strong force, it's always permanently confined. So basically, maybe monopole, anti-monopoles are always permanently confined into like pairs, right? And then these could form dark matter. These could form the dark matter, or yeah. So you could have dark matter like that. They're just bound monopole, anti-monopole pairs that are permanently confined together. And so my advisor and I were like, oh, okay, well, we should write a paper on that, but people already thought about it. So like, so then, yeah, but there are people. It's called, those systems are called monopolium. You like that venture, right? Monopolium, and basically the idea is if they're the dark matter, there's this sort of sea of monopolium that permeates the cosmos. So probably not true, but anyway. All right, we still have some cookies and stuff. So thanks for coming. Oh, yeah, and the next talk, next Friday, same place. and it's going to be Dr. Ettore Vitale, who's going to tell us about the mysteries of quantum mechanics. So